And so for phase separation to occur in our liquid mixture, the delta G of mixing for the system has to look something like this. Okay? All right, and so that graphically, this is, how we could analyze the system. But now let's go for a more analytical approach. Okay? And so in our analytical approach, the two sort of things we want to figure out are how much of species 1 is in each phase. So not only, the mole fractions, but we legitimately just want to know like how many moles of species 1 is in the alpha phase and how many moles of species 1 is in the beta phase. So that's one thing we want to figure out. And then also what the mole fractions are. What are x1 alpha and x1 beta? Oh, so let me rewrite this as how many moles 1 are. Okay? All right. And so to figure that out, we need to, define what our criteria are for phase separation, for liquid-liquid phase separation in our system. So criteria for finding x1 alpha and x1 beta are that, as I mentioned, the slopes at the x1 alpha and at the x1 beta phase in the delta G mixing curve, they're equal, right? And that's essentially a proxy for saying that the chemical potentials of species 1 in the alpha phase, that chemical potential is equal to the chemical potential of species 1 in the beta phase. So that's one sort of constraint or criterion that has to be satisfied. And the second one is more fundamental, and it's that the material balance must be obeyed. So the amount of moles of species 1 in the alpha phase plus the amount of moles of species 1 in the beta phase has to be equal to the total amount of moles of species 1 in the system. Okay. All right. So now that we have those two criteria in hand, what we want to do is apply them. All right, and so the first thing we're going to do is we're going to bring it back to MEV1, and we're just going to start with a material balance. Okay, and so in our system, it's a closed system, and there's no reaction. And so in the end, what we're going to see is that the initial amount of species 1 in our system is equal to that final amount. The initial amount is the total moles in our system times that x1 naught, right? And so x1 naught was this middle composition that we picked here. The final amount of species 1 is going to be the number of moles of species 1 in the alpha phase, or the number of total moles in species 1, so this includes both species 1 and species 2, and I should say that this n is also total moles. So that includes species 1 and species 2. Anyway, so we have n1 alpha times x1 alpha plus n beta times x1 beta. Okay, so this product gives us the moles of species 1 in the alpha phase. This product gives us the number of moles of species 1 in the beta phase. So total moles in beta. All right, and so if we go back to our material balance statement, what we have is this. And we could rearrange this equation so that we get x1 naught is equal to n alpha over n x1 alpha plus n beta over n x1 beta. Alright, I'm now going to define some new parameters. And so here we have n alpha over the total moles of n, right? So the portion of the moles that are in the alpha phase over the total moles in our system. And that's essentially a mole fraction, or that is a mole fraction. And so I'm going to call this mole fraction F alpha. Similarly, I'm going to call this mole fraction F beta. And we know that F alpha plus F beta has to equal 1, right? Because this is telling us the fraction of total moles in the alpha phase plus the fraction of total moles in the beta phase. And since we only have two phases, those fractions need to equal 1. All right, and so what we have here is we could rearrange these equations so that we get F alpha is equal to x1 beta minus x1 over x1 beta minus x1 alpha, and F beta is equal to, not here, x1 naught minus x1 alpha over x1 beta minus x1 alpha. Okay? Alright, and so we have these two equations that tell us the fraction of moles, total moles, that are in the alpha phase and the fraction of total moles that are in the beta phase. And so this pair of equations have a special name. This is known as the lever rule. Okay? And so essentially, you use the lever rule when you want to determine the fraction of total moles in the alpha and beta phases. Okay? And so, following that, if you wanted to figure out the total moles of species 1 in the alpha phase, what you would do is you would take your total moles, which you could figure out based on the volume of your system. You would take n times F alpha times x1 alpha. And that would give you the number of moles of 1 in the alpha phase. Okay? And then, if you wanted to figure out the number of moles of species 1 in the beta phase, you would just do or calculate this product. Okay? Alright, and so that's using the lever rule, you could figure out at least the molar amounts of species 1, and you could do the same thing with species 2 as well. You could figure out the molar amounts in the alpha and beta phases.